Hello everyone. In this video, we're going to be covering concepts from the course of Chemistry 1412, also known as General Chemistry 2. So the topic that we're covering is going to be the laws of thermodynamics and calculating entropy. Thermodynamics is the study of heat and temperature and how it relates to energy and work. In this video, we're going to be talking about the first three laws. So the first law, second law, and third law, and how it's going to actually relate to our course and to entropy. Spontaneous change is our first topic. A spontaneous change is one that occurs without a continuous input of energy from the system. So this is going to be something that occurs naturally. So an example would be iron rusting. So in our picture, we have an iron nail. By simply putting it outside, we're able to oxidize that iron and rust will naturally form. So this would be considered a spontaneous change. All chemical processes require energy or activation energy to take place. However, once a spontaneous change begins, there's no further input of energy that is needed to allow this process to continue. Spontaneous change can be exothermic and endothermic. Exothermic, remember, is when heat or energy is released from the system. So we're losing heat from our system. These are going to be processes such as freezing or condensation at a low temperature, combustion reactions, and oxidation of iron and other metals. The second is endothermic, which is where heat is coming into our system. And that's going to be processes such as melting and vaporization at high temperatures and dissolving of most soluble salts, where delta H doesn't predict the direction of the spontaneous change by itself. The second topic is non-spontaneous change. A non-spontaneous change can occur only if the surroundings continuously supply energy to the system. So an example is going to be water boiling. So the moment I take that heat away from the water, it's going to stop boiling. So I have to continuously supply heat in order for the water to continue to boil. This would be considered a non-spontaneous change. It will not occur naturally on its own. If a change is spontaneous in one direction, it will be non-spontaneous in the reverse. So if I think about my spontaneous change of the nail rusting, so in our forward direction, we put a nail outside, it oxidized and it rusted as our product. But if I want to move in the reverse direction, it won't naturally remove its own rust. I have to put in energy or put in heat in order for that rust to be removed from the nail. So that explains why it's spontaneous in our one direction, but non-spontaneous in the opposite direction. And now we can cover the first law of thermodynamics. It states that energy is conserved. It is neither created nor destroyed, but is transferred in the form of heat and or work. And we can use the equation delta E equals Q, which is heat, plus W, which is work. The law of conservation of energy applies to all changes and does not allow us to predict the direction of spontaneous change. And so I have a brief little picture right here of our system, which is going to be our beaker. And it's going to explain this equation a little bit more. So if I'm putting work into my system, my delta E will be positive. If I have the system performing work, our delta E will be negative. And then when we move over to heat, if heat is being removed from the system, our delta E is negative. And if heat is being added to the system, our delta E is positive. And so I have one more example of the first law of thermodynamics. So remember, the law stated that heat isn't created or destroyed, but it's transferred in the form of heat or work. And the light bulb, or a lamp in which the light bulb is in, is a perfect example of the first law. So we are going to be moving from electrical to thermal to radiant energy throughout the process of the energy going into the lamp and into the light bulb. So the moment I plug in my plug to the electrical socket, we have electrical energy. Inside the light bulb, it is transferred into thermal energy, and as that heat comes off of the light bulb, I now get radiant energy. So, nowhere in that light bulb or that lamp is energy created or taken away. It's simply transferred from one form to the next, so from electrical to thermal to radiant. The next topic is freedom of particle motion. All spontaneous endothermic processes result in an increase in motion or freedom of motion of the particle in the system. So, as you can see, we're going from solid to liquid to gas. As I move from solid to gas, I have less freedom of particle motion, which makes sense. Our particles are more condensed in a solid form, and they have more freedom as you move to a gaseous form. You also, going from solid to gas, have localized energy of motion, and because, once again, it is more condensed in a solid form, and you have dispersed energy of motion, so the particles are able to move more, so you have a wider area of energy of motion as we move into our gas phase. These are going to be really important to take into consideration whenever we're working with entropy. A change in freedom of motion in particles in a system is a key factor affecting the direction of a spontaneous change. So now we're going to talk about microstates and dispersal of energy. In a system, its energy is constantly being redistributed due to change in the location and the energy of molecules due to their collisions. The arrangement of the energy of each molecule in one instant is called a microstate. And we'll be able to see how those are taken into consideration when we're calculating entropy. The number of microstates, which is represented with a W, in a system is related to entropy, which is S, of the system. So our formula for entropy is going to be S equals K, which is Volt's constant, provided right here. So 1.38 times 10 to the negative 23 joules per Kelvin to the negative 1. Ln of W, W being the number of microstates that we have. A system with fewer microstates has a lower entropy, and a system with more microstates will have a higher entropy. All spontaneous endothermic processes exhibit an increase in entropy. Entropy, like enthalpy, is a state function and is therefore independent of the path taken between the final and initial states. So let's talk about spontaneous expansion of a gas. So we have a picture here, and we have two, let's call them flasks. In our example A, we have a gas filled in one of our flasks, but our stop clock is closed, preventing it from moving into our empty flask. And in part B, we have the gas in both sections evenly distributed between both flasks once the stop clock is open. So when the stop clock is open, the gas spontaneously expands to fill both flasks. Increasing the volume increases the number of transitional energy levels the particles can occupy. The number of microstates and the entropy will also increase as we do this. And now we're going to talk about the second law of thermodynamics. All real processes occur spontaneously in the direction that increases the entropy of the universe. For a process to be spontaneous, a decrease in entropy of the system must be offset by a larger increase in the surroundings. The sign of delta S, so the change S for a reaction does not by itself predict the direction of spontaneous change. So if we want to know the change in entropy of our universe, we have the change in entropy of our system plus the change in entropy of our surroundings. And for it to be spontaneous, our change in entropy of our universe has to be greater than 0. Comparing energy and entropy. The total energy of the universe remains constant. So delta E of the system plus delta E of the surrounding will be delta E of our universe, which will be equal to 0. So they will balance each other out. Delta H is often used to approximate our delta E. For enthalpy, there is a no 0 point. We can only measure changes in enthalpy. The total entropy of the universe will increase. So our delta S is always going to be greater than 0, while our delta E for the universe will be equal to 0. For entropy, there is a 0 point, and we can determine absolute entropy values. So that's what the main difference between enthalpy and entropy is. So make sure you don't get confused between the two terms. And now let's cover the third law of thermodynamics. A perfect crystal has flawless alignment of all its particles. At absolute 0, the particles have minimum energy, so there's only one microstate. So our our S equals K ln of W. So K ln of 1, which will equal 0. So our S of our system equals 0 at 0 degrees Kelvin. To find the entropy of a substance at a given temperature, we cool it as close to 0 degrees Kelvin as possible. We then heat in small increments, measuring the Q and the T, which is our temperature, and calculate the delta S for each increment. The sum of these delta S values gives the absolute entropy at the temperature of interest. And now we'll cover standard molar entropies, which is S naught, or some people will say S to the 0, but this is also referred to as naught. Is the standard molar entropy of a substance, measured for a substance in its standard state in units of joules per mole Kelvin. The conventions for defining a standard state includes 1 atm of gas, which is its pressure, 1 molar for solutions, and the pure substance in its most stable form for solids and liquids. So 1 atm of gas for gases, 1 molar for solutions, and a pure substance for solids and liquids. There are some factors that affect entropy, and they're very important to take into account when you're looking or comparing different circumstances. Entropy depends on temperature. For any substance, S naught increases as our temperature increases. So they are parallel to each other. So as one increases, the other will increase as well. Entropy depends on the physical state of a substance. S naught increases as phase change moves from solid to liquid to gas. So that is something very important to take into consideration. The formation of a solution affects entropy. And entropy is related to the atomic size and the molecular complexity. Remember to compare substances in the same physical state. So as it becomes more complex, or the atomic size increases, the entropy will also increase. So let's work through an example to where we have to compare and contrast different situations. to determine which one shows a decrease in entropy. So for part A, we have O2 gas at 300 Kelvin moving to O2 gas at 400 Kelvin. So we have an increase in temperature. By increasing our temperature, this was a factor that also increases our entropy, which means A can't be one of our answers here. For B, we have H2O solid at 0 degrees Celsius goes to H2O liquid at 0 degrees Celsius. So our temperature isn't changing, however, our state is. We're moving from solid to liquid. And remember, moving from solid to liquid to gas will increase the entropy. So B also is not an answer. For C, we have into gas at 25 degrees Celsius going to into aqueous at 25 degrees Celsius. So the temperature is not changing, the state is. We're going from gas to liquid, which is aqueous. It's a substance mixed with water, which makes it aqueous. So we're going backwards. We're not going from solid to liquid to gas. We're going from gas to liquid. So this would be a decrease in entropy. So right now we think C could be our answer, but let's go through the rest of the answer choices to ensure that we're not making a mistake. For D, we have in H3 liquid at negative 34.5 degrees Celsius goes to NH3 gas at negative 34.5 degrees Celsius. So the temperature is not changing. Again, the state is changing. And from solid to liquid to gas, and in this situation, we're going from liquid to gas, we are increasing our entropy. So D is not our answer. And so we move to E. So we have 2 H2O2 gas going to 2 H2O gas plus O2 gas. So what's changing here is the number of moles. So the complexity or the structure. So we're going from 2 moles, which we know from the coefficient, to 3 moles, which is the 2 plus the 1 that is here. So because we're increasing from 2 to 3 moles, we are increasing our entropy. So E cannot be our answer either. So the only one that fits that is decreasing in entropy is going to be C, because we're going from gas to liquid. And now we can talk about entropy changes in the system. The standard entropy of reaction, delta S naught, is the entropy change that occurs when all reactants and products are in their standard states. So delta S naught equals the sum of the M S naught of products, so this is times how many moles, minus the sum of our reactants, where M and N are both the amounts of moles of products and reactants. They simply just define them as different letters, but they're going to be pretty much the same thing, given by the coefficients of the balanced equation. So for this, ensure that your equation that you're using is balanced before plugging in your numbers. So let's work an example. Elemental boron can be formed by reaction of boron trichloride with hydrogen. If delta S naught equals 80.3 joules per Kelvin for the reaction above, what is the S naught for BCl3 in grams? So let's take a look. Sorry, not in grams, it's just the substance in gas form. So we have already what appears to be a balanced equation. We have BCl3 gas plus 1.5 H2 gas yields B solid plus 3 HCl gas. And then they brought down the substance, because this is normally how we're going to write it out, or we'll see it. And they gave us our S naughts for all our other substances, and they want to know it for the BCl3. So let's move over to our boogie board so that we can begin to write this example out. So we can use the equation. Let me move my mouse for you. All right, so the equation that we have to use is delta S naught equals the sum of our products minus the sum, it's writing sideways, there we go. There we go, okay. So delta S naught equals the sum of our products minus the sum of our reactants. All right, so we have to, let's go ahead and rewrite out the information they provided so we kind of know what has to be plugged in. So we have BCl3 plus 1.5 H2 yields B plus 3 HCl. And then the S naughts, we don't know what BCl3 is, that's what we're looking for. For H2, we have 130.6. For B, we have 5.87. And for HCl, we have 186.8. So let's figure out what we do. We can set it up where delta S equals our products. So we have to take into consideration how many moles. So for B, it's 1 times the value that was provided. So 1 times 5.87 plus, because we're trying to find the sum of our products, 3 times 186.8. And that's going to be for our products. So you take the moles times the value. And that is minus our reactant, so I'm going to write it down here. So we have 1 mole times X, because we don't know what this number is and we need to find it, plus 1.5 times 130.6. And that's our reactants. And we also know one other thing. We know that our delta S naught is going to be 80.3. And so now what we have to do is solve for what we know, and then we have to determine what this X value is. So let's begin to simplify. So we have 80.3 equals, when you simplify the products, so you multiply 1 times 5.87 plus 3 times 186.8, you'll get 566.27. So this is our products minus our reactants. So 1 times X, so X plus 1.5 times 130.6 will give you 195.9. So this is what we have so far. So now we can simplify even more. So I want to get rid of this negative, so I'm just going to go ahead and move it over. So I'm going to add X plus 195.9 to both sides. So I'm going to do the same thing over here. So I'll end up with 80.3 plus X plus 195.9 equals 566.27. You can either add these two together, or you can do them in separate steps. I did it in separate steps, but it doesn't make a difference. So I went ahead and I subtracted 80.3 minus 80.3. So I got X plus 195.9 equals 485.27. And then I subtracted 195.9 from both sides. and I ended up with x equals 290.07. So this is going to be our S naught for BCl3. So you simply multiply the moles times whatever the value is for the products first, minus the reactants. Make sure that you don't flip them. It's a common mistake students make. So products minus reactants, and then that will give you your delta S naught. Or you can plug it in and solve for a variable of an unknown, which is what we did here. So let's go back to our PowerPoint. Now we're going to talk about predicting the sign of delta S naught for the reaction. We can often predict the sign of delta S naught for processes that involve a change in the number of moles of gas. So for instance, N2 gas plus 3H2 gas yields 2NH3. So we're moving from 4 moles to 2 moles of gas. Delta S naught is positive if the amount of moles increases. So going from this example of 1 mole, because we don't take into consideration the solid, so 1 mole of gas moving to 2 moles of gas. So we're increasing in moles of gas. Delta S naught is negative if the amount of gas decreases, such as in this example. So we went from 4 to 2. So our delta S would be negative. So let's do an example. Which relationship best describes delta S naught for the following? So we have 2H2S gas plus 3O2 gas yields 2H2O gas plus 2SO2 gas. So we're going from 5 moles to 4 moles. So because we're moving from 5 to 4, we know that we're going to have a negative value. Or if you want to do it the math way, so if you take the moles, so our product, which is 4 moles, and we subtract how many moles our reactant had, which was 5, we get a negative number. We get a negative 1. So it would make sense that our delta S naught would be less than 0 because it would be a negative number. Now we're going to talk about entropy changes in the surroundings. A decrease in the entropy of the system is outweighed by an increase in the entropy of the surroundings. Sorry, I want to make sure I said that correctly. A decrease in the entropy of the system is outweighed by an increase in the entropy of the surroundings. The surroundings function as a heat source or as heat sinks. In an exothermic process, the surroundings absorb the heat released by the system, and S of our surroundings will increase. So when Q of the system is less than 0, so it's negative, when Q of our system is greater than 0, so it's positive, and when delta S of our surroundings is greater than 0. It is an exothermic process. The surroundings provide the heat absorbed by the system, and the S of the surroundings will decrease. So our delta, or sorry, not delta, Q of our system is greater than 0, or our Q of our surroundings is less than 0, and our delta S of our surroundings is less than 0. So they're pretty much the exact opposite of each other. So one, with an exothermic, the Q of our system is going to be less than 0 because we're giving heat off. While an endothermic, we're gaining heat, so it's greater than 0. For the surroundings, exothermic, the heat is going into the surroundings, so it's greater than 0. But for endothermic, we're taking heat from the system, so it's less than 0. And then the delta S for the surroundings will also correspond with the Q from our surroundings. Now, temperature at which heat is transferred. Since entropy depends on temperature, delta S naught of the surroundings is also affected by the temperature at which the heat is transferred. For a reaction, our Q of our system is going to be equal to a negative Q of our surroundings. The heat transferred is specific for the reaction, and is the same regardless of the temperature of the surroundings. The impact of the surroundings is larger when the surroundings are at lower temperatures because there is a greater relative change in the S of our surroundings. So our delta S of surroundings equals negative Q of the system divided by our temperature. Or we can say that our delta S of our surroundings equals negative delta H of our system divided by temperatures. And this is going to be for processes at a constant pressure. Delta S in equilibrium state. For any processes approaching equilibrium, our delta S naught of our universe is going to be greater than 0. At equilibrium, there's no further net change, and delta S of our system is balanced by delta S of our surroundings. So our universe will be at 0, and the system and the surroundings will balance each other out to equal 0. So the system and the surroundings will be equal to each other when they're inverse. So one will be positive while the other will be negative. When a system reaches equilibrium, neither the forward nor the reverse reaction is spontaneous. So there's no net reaction in either direction. And that's pretty much everything we have to cover today. So I hope that this was helpful. If you're still struggling with this topic, I highly suggest that you go to a website called Khan Academy. So let me go ahead and spell that out for you. So it's Khan Academy, and you can type in either thermodynamics or entropy, and they can come up with some more examples. Just do remember that when you're calculating your entropy, it is going to be your products, the sum of your product, minus the sum of your reactants. If you do it the opposite direction, it's not going to work out. It's going to give you a completely different number. However, there are sometimes tricky professors that will throw in that answer on a test. So double check your work, try to write every single step down so that you can check to make sure you did your steps and your processes properly. That is all I have today. Thank you and best of luck on this concept.